Welcome to this explainer. Okay, I am absolutely thrilled you're here today because we're diving into something that is simultaneously one of the most exciting and, let's be honest, most frustrating frontiers in software right now, maximizing the true potential of local AI models. Look, we've all seen the incredible promise of having a powerful AI running right on our own machines. But if you've actually tried to use them to build complex software, you know they can quickly hit a brick wall. So today, we're going to explore this fascinating framework called microswarm, which acts as the ultimate remedy for the limitations of local AI. We're going to break down exactly how it works and the architecture behind it. Settle in, and let's get started. To understand the cure, we really have to understand the disease first. And it brings up a critical question. Why exactly do local AI models hallucinate on big tasks? Now, we aren't talking about massive cloud-based models here. We're talking about highly capable, smaller models, like your 35 billion parameter local setups. These models are incredibly smart, no doubt about it, but they suffer from a severe, almost debilitating condition known as memory drift when you hand them heavy, monolithic developer tasks. You ask them to build an entire feature, and halfway through, they just forget the constraints you set in step one. They start hallucinating variables, they lose the plot of the architecture, and eventually the code they spit out is a tangled, broken mess. It's a massive pain point if you're trying to build autonomous local systems. So to unpack how we solve this, here's our roadmap for today. First, we'll look at the local AI problem. Second, the microswarm solution. Third, the four-phase workflow. And finally, under the hood mechanics. Okay, let's dive right into part one, the local AI problem, specifically dealing with monolithic tasks. Think about what we're actually demanding from our hardware here. A 35 billion parameter AI model is powerful, sure, but its execution context, its working memory, has very real hard limits. When you give it a massive task, it's literally like asking someone to carry a giant, oddly shaped 1,000-pound boulder up a huge hill. It is just too heavy and completely unmanageable. The model is trying to hold the overarching goal, the syntax rules, the file structure, and the specific logic all in its head at the exact same time. Inevitably, that execution context gets overwhelmed. The result? Inevitable hallucinations and memory drift. The AI starts making things up because it literally cannot retain the entirety of that monolithic task from start to finish. We are setting our local models up for absolute failure by giving them the wrong shape of work. Which brings us to a much better way of doing things. Let's look at part two. The microswarm solution. And honestly, this is nothing short of a paradigm shift. The core philosophy of the microswarm framework boils down to one word: microsegmentation. If the problem is that the boulder is too heavy, well, the solution isn't to build a stronger AI model. The solution is to smash that boulder into easily carried pebbles. Microsegmentation means taking that large monolithic development task and systematically segmenting it into a strictly linear dependency chain. But we're not talking about just any chain here. We're talking about a chain of very small, highly deterministic single assertion phases. We are radically limiting the LLM's execution context. By giving the model only one tiny hyper-focused pebble to carry at a time, its attention remains completely locked in. It simply doesn't have the space or the cognitive load to drift or hallucinate. It executes one microstep perfectly and then moves to the next. So how exactly do we smash that boulder? Let's move to part three, the engine blueprint, and look at the four-phase workflow that makes this whole thing possible. Let's see how this builds a completely foolproof system. In the microswarm framework, a single parent task is never just handed to an AI to figure out on its own. It is rigidly chopped up into four enforced phases. Every single task must go through this exact linear chain. First, research, denoted by an R. Second, discovery, or D. Third, TDD red, that's test-driven development red, denoted by T. And finally, TDD green, denoted by I for implementation. The AI model is never allowed to jump straight to writing implementation code. No way. It is forced down this strictly linear pipeline, carrying one single pebble at a time. What's really fascinating here is the sheer level of discipline this introduces to AI development. Every phase has a very specific target deliverable, a concrete verification method, and a specific skill tool injected right into the AI's prompt. Let's break it down. In the research phase, the AI isn't touching code. It's writing a research.md document, verified by checking for proper sections, using an injected tool called using superpowers. Once that is verified, it moves to discovery, where it maps out exactly what will be tested by writing a testplan.md. Then comes the magic. In TDD Red, the AI writes a failing test. Let me repeat that. It doesn't write the app code yet. It writes a test for a single assertion using the test-driven development tool.
And finally, in TDG Green, the AI writes the absolute minimum source implementation required to make that one specific test pass. This framework essentially orchestrates the AI to act like the most disciplined senior developer you've ever met in your life.
Now, the crucial point is how this framework actually knows if the AI succeeded. It doesn't use another AI to just guess or vibe check if the code looks good. It relies on pure deterministic verification. Look at the stark contrast between these steps. When the AI finishes the TDD red phase, writing that failing test, the framework automatically runs the test suite. It strictly asserts that the test runner must return an exit code of 1. It absolutely must fail. If it doesn't fail, the AI messed up the test, and it has to go back and do it again. Conversely, in the TDD green phase, after writing the minimal implementation, the test runner is executed again. But this time, it rigidly asserts an exit code of 0. The test must pass. By verifying exact mathematical exit codes, rather than relying on vibes or LLM self-reflection, the microswarm framework guarantees that every single step rests on a totally solid foundation before moving to the next. I know it sounds amazing in theory, but running multiple AI agents concurrently on a local machine, doing all of this file writing and testing, that could be a total disaster. So let's move into our final section, under the hood, to see the genius technical mechanics that prevent absolute chaos. To orchestrate a swarm of microtasks effectively, you need a background watcher loop that manages your resources. When the orchestrator assigns a phase to an AI worker, it creates a completely isolated workspace. To start, it leverages isolated Git work trees for concurrent runs. This means Worker 1 is never going to accidentally overwrite Worker 2's files. They are safely sandboxed. But here is the really clever part. If you're constantly creating new work trees, you definitely do not want to copy a massive Python virtual environment with gigabytes of dependencies every single time. That would grind your machine to an absolute halt. Instead, the framework automatically symlinks your local .venv directory right into the new work tree. This brilliant little trick completely avoids copying massive dependencies while still enabling the AI to instantly invoke relative test commands like .vem/bin/pytest and have them resolve perfectly inside its isolated sandbox. Another massive under-the-hood advantage is how we actually talk to these local AI models. If you've spent any time prompting, you know that standard prose guidelines, just writing a paragraph telling the AI what to do, are highly unreliable. Local models are incredibly prone to misinterpreting long, flowing prose. The microswarm framework completely bypasses this issue. Instead, it relies on explicit skill tool calls. Right at step 0 of the prompt workflow, the framework injects specific JSON-like tool instructions, things like writing plans or test-driven development. Because modern local models are specifically trained to parse and execute function calls and tool instructions, they handle these explicit skill tools with significantly higher reliability than just reading a block of text. It literally forces the AI into a strict execution mindset rather than a chatty conversational one. And that brings us to the end of our deep dive. We've seen exactly how 35 billion parameter models can totally crumble under massive tasks due to memory drift, and how the microswarm framework solves it by using strict microsegmentation, that rigid research, discovery, TDD red, TD green workflow, plus isolated Git work trees and skill tool injection. The problem completely vanishes. It turns out that by boxing the AI in, by giving it highly rigid deterministic constraints, we actually unlock its true capability to build complex software reliably. So I'll leave you with this final, provocative thought to ponder today. If strict constraints and microsegmentation are the actual keys to unlocking true autonomous local AI development, how will this framework change what you build next? Thank you so much for joining me for this explainer. I really hope this structure helps you tame those local AI models. Keep experimenting, and I will see you next time.